This question is from GATE 2020 Mechanical Engineering paper set 1, question number 46. The thickness of a steel plate with material strength coefficient of 210 megapascal has to be reduced from 20 millimeter to 15 millimeter in a single pass in a 2 high rolling mill with a roll radius of 450 millimeter and rolling velocity of 28 meter per minute. If the plate has a width of 200 millimeter and its strain hardening exponent N is 0.25, the rolling force required for the operation is dash kilonewton. It has to be rounded off to 2 decimal places. There is a note also mentioned here which gives the formula for average flow stress, which is nothing but material strength coefficient into true strain raised to N divided by 1 plus N, where N is the strain hardening exponent given to be 0.25. Let's find out the rolling force. So we'll start by listing out the given things. Material strength coefficient is given to be 210 megapascal. Strain hardening exponent N is 0.25. Initial thickness denoted by HI is 20 millimeter. The final thickness given is 15 millimeter. Roll radius capital R is 450 millimeters. Roll velocity small v is 28 meter per minute. Width is given to be 200 millimeter. And we need to find out the rolling force. Let's denote it by F. So rolling force will be simply given by average flow stress. Let's write it as sigma average into the projected area. We need to find out both these terms, both of these quantities in order to find the rolling force. So first one, we'll aim for finding out the average flow stress. As per the given formula, it is material strength coefficient, which is 210 megapascal, into the true strain. Let's denote it by epsilon to the power n divided by 1 plus n. And n is given to be 0.25. So this will be 210 times epsilon raised to 0.25 divided by 1 plus 0.25. So to find average flow stress, we will have to find out true strain epsilon. Epsilon true strain by its definition is nothing but natural log of final length upon initial length. Now we don't know the final and initial lengths, but we do know the final and initial thickness of the slab, and we know the width. Also we know that width remains same. Width does not change. Now volume of the material that passes through the rolls will be remaining same. So we can write capital V initial is equal to capital V final. Capital V is nothing but the volume of the slab passing. This volume can be written in terms of length, breadth and height. So it will be simply Li, Hi, Bi, which is nothing but B, will be equal to Lf, Hf into Bf is nothing but B again, because width remains same. So B from both sides can be divided and we'll get Lf upon Li will be equal to Hi upon Hf. So this ratio is nothing but 20 by 15. We can reduce it as 4 by 3. This gives us the true strain. So true strain here becomes natural log of 4 by 3. The value we get is 0.28768. This can be rounded off to 3 decimal places, 0.288. Now that we have the value of true strain, we can find out the average flow stress. So average flow stress will be equal to, it is 0.288 raised to 0.25, which is 210 into this value 0.288 to the power 0.25 turns out to be 0.732 divided by 1.25. So we get our value of average flow stress as 123.037 megapascal. Let me just highlight this. This is the value of average flow stress. Now second thing that we need to find out is projected area. Let's find that out. Projected area is given as projected length into the width B. So here we need to find out the projected length, and this value projected length, let's denote it by L, is given as under root of change in thickness, which is delta H, into roll radius capital R. This is a standard formula you must know. So this will be equal to under root of change in thickness is 20 minus 15, which is 5 millimeters, into roll radius is 450 millimeters. So projected length is nothing but 47.43 millimeters. And just putting this into the formula for projected area, we will have projected area is 47.43 into width is 200. Pay attention while putting the values. Width is 200 millimeters, and here we took the roll radius value, which is 450 millimeters. So projected area turns out to be 9486 millimeters square. Let's put all these values in the formula for rolling force. So we will get rolling force F is equal to 123.037 into 9486, which is equal to, so in Newton we get the value as 1167062.58, but we anyway have to write the answer in kilonewton. So after dividing by 1000 we'll get the answer of rolling force. Let me write here in the bottom, rolling force is equal to 1167.06 kilonewton. So let's go back and fill in this answer. The rolling force required for the operation is 1167.06 kilonewton. To learn about flow stress in detail, you can refer to the NPTEL video, Lecture 10 Flow Stress. It's from the course Mechanical Behavior of Materials 1. The course is taught by Professor Shashank Shekhar. He is from Department of Materials Science and Engineering of IIT Kanpur. I hope this helps clearing your doubt. Thank you.